Lesson 10.2, Logarithms and Logarithmic Functions. Now we're going to have to get used to a notation that used to be quite common, but is long since been, and that is logarithmic notation or logarithms. And it's very important to understand that logarithms is an old-fashioned name for exponents. Okay, so when you take the logarithm of something in your calculator, it's going to give you an exponent. And we'll get to that in a minute. There are two main forms for logarithms. We have logarithmic form and its equivalent exponential form. Now, this is not an equation, this is just equivalent statements. When you take the log of something, what you get out of it is an exponent. It's an exponent of the base. So you take the base to a power, and that's going to give you x. So three things, three positions. There's a couple of rules. b, the base, has to be greater than 0. It cannot be equal to 1. And x, you take something to a power, what you get out of that is a positive answer. Now let's go from logarithmic notation to exponential. Here's our base, 8. So you take the log of something, your answer is the power. And that gives you 64. If I go in the order that they had it, it would look more like this, just the other way around. Next one, again, 4 equals the base, which is 16, and the answer is our exponent. So the base to the power, and there's x. These are all true statements, just as writing them in different form. When you have letters, you can still do it though. Again, you have 7 equals the base, and the base is subscripted. Notation there is q, and the answer you get out of a logarithm is an exponent. So there's t. Here's a more complex one. You have a squared plus b squared. The base is x plus 2, and it's being taken to the st power. Okay, that's from logarithmic to exponential. Now let's go the other way. Alright, we have log. The base is 27, so subscripted 27. 3 equals the exponent. So here's the base. The power is what you get as a result of taking a logarithm. And there's x. So here we have log base 10 of 100 equals 2. Try that in your calculators, you will get that answer. Because your calculators are automatically and defaulted to base 10. Now we could write it this way, or you can actually write log 100 equals 2. Without a number here, it's assumed to be 10. Next one, we have log of 12, and its base x equals the exponent a. Next one, we have log of 84x plus y. Base, right here, this base would be a plus b equals the exponent, 7x. Alright, now let's evaluate. Now your calculators can actually do log of 100. All you have to do is punch in log of 100 and you will get 3. If we didn't have the calculator, we would say 10 to what power gives us 1,000? And that would be 3. Our calculators cannot do this one because it cannot do base 2. But if we change it to exponential notation, it will make sense to us. 2, now notice we don't have it equal to anything here. So that means 2 to some power, because that's what the logarithm will give you, the exponent, but we don't have it, will give you 8. Written this way, we can actually realize that it's 3. Next one we have base 9 to what power will give us 3? And that is the square root of 9, so 1/2 power. Next one we have base 8 to some power. It's going to give you -5. Well, this is x, and we said that you cannot have an x that's less than 0. So this one is undoable. Next one is 8 to what power gives you 1 for an answer. That would be 0. Anything to the 0 power is 1. Now, inverses are what cancels things out. If you remember, division is the inverse of multiplication, and so on. So, if we rewrite this one from logarithmic to exponential, okay, they say it's equal to something. We don't know what it's equal to. So we'd say 6 to what power gives you 6 to the 8th. So all of this goes right here. Here's your base. That's right here. And if you look at this, it looks like the questions we did in 10.1. What is this going to be? Well, it must be 8. So what happened was log base 6 of 6 basically canceled itself out. It's the same base. This one, same idea. Now, this is a very complex looking exponent. Okay, but let's just say it looks like this. 3 log 3 of x. These two things are inverses of each other. Just like when we have log base 6 of 6. And these will cancel each other out. Now I have x there to make it look simple, but here we have 4x minus 1. So what will happen is they will cancel out, and we'll be left with 4x minus 1. We'll come back to that tool later. All right, let's solve this. We don't know what n is, so we'll say 8. Now the answer for a logarithm is the power equals n. And we can calculate that out on our calculators. 8 to the 4/3 power, which is nice. And that is 16. Next one, 27. The answer, when you take a log of something, is the exponent. And this one will give you 9. How about inequalities? Do they work? Well, they give us an important piece here to follow. This is exponential form, and this is how it would look in logarithmic form. If you follow that order, or in exponential form, excuse me. If you follow that order, then you'll be fine. Here we have a less than. Here's our rules for less than. Remember, x can't be less than 0, so you have to plug that in to keep it in check. So 6 to the 3rd power. Oh, I'm going to rearrange that. Sorry, I have a habit of going in the other order, so I'm going to stay in their order. So x is greater than base 6 to the 3rd power. So x is greater than 216. Next one we have x is less than base 3 to the 2nd power. X is less than 9, but it cannot be negative, so you add on this greater than 0 part. And that ends lesson 10.2. This last part here is real quick. It's just the obvious. If you have the same logs, then you can just ignore them, and you have x equals 7. And it works with inequalities as well. X is greater than 7. So we are ignoring the logs just like we ignored the bases. And that now ends lesson 10.2.